For many years, something unusual has been happening at the edge of our solar system. A group of icy objects far beyond Neptune's orbit appears to be drifting in the same direction. Their orbits are aligned in such a way that it almost looks as if some massive object is herding them, forcing them into a clustered pattern. Such orbital alignment is statistically very unlikely without an external gravitational influence. And no, it isn't Neptune, and it isn't Pluto. It's something much farther away, far more massive and completely hidden. Astronomers call it Planet 9. A mysterious world that could be 5 to 10 times more massive than Earth, orbiting so far away that sunlight barely reaches it. And the most intriguing part is that new clues are emerging from old data, new discoveries, and strange objects that might finally point to where it is hiding. Or perhaps we've been wrong this whole time. Has Planet 9 actually been spotted already? Or is this the greatest scientific ghost hunt of the last decade? Let's take a closer look. Back in 2016, something unusual caught the attention of two astronomers, Mike Brown and Konstantin Batygin. They weren't searching for a new planet. They were simply trying to understand why certain objects in the outer solar system were behaving so strangely. These were not planets and not comets. They were objects that today are known as extreme trans-Neptunian objects, frozen fragments orbiting far beyond Neptune. But the strange part was this. Many of them had orbits that didn't appear random. Instead of being scattered chaotically in every direction, their trajectories seemed grouped together. Their orbits were tilted in almost the same way and appeared to point toward roughly the same region of space. That shouldn't happen. In a stable solar system, small bodies that far away should have chaotic and widely scattered orbits, not neatly aligned ones. The only explanation that made sense at the time was simple. Something massive was pulling on them gravitationally, something we hadn't seen yet. Brown and Batygin ran the calculations. If this mysterious planet really existed, it would have to be at least 5 times more massive than Earth, and possibly as much as 10. And its orbit would be enormous, roughly 400 to 800 times farther from the Sun than Earth's orbit. For comparison, Neptune lies only about 30 times further from the Sun than Earth. In other words, this object wouldn't just be distant, it would exist in a region of the solar system that we have barely explored. They called it Planet 9, not only because it would be the 9th planet after Pluto's reclassification, but also because no other explanation seemed to fit the data. And interestingly enough, this hypothesis came from Mike Brown, the very scientist who became famous for helping remove Pluto from the list of planets, a bit ironic. But this wasn't just a bold claim. They didn't propose the existence of Planet 9 for headlines. In their scientific paper, they presented detailed mathematical calculations. The work showed how the gravitational influence of such a hypothetical planet could explain the clustered orbits of these distant objects. Moreover, the researchers suggested that it might also explain some of the unusual orbital tilts of other known objects. For example, why some of them move at very strange angles. This idea sparked a global search. Telescopes began scanning the skies in an attempt to find this invisible giant. Astronomers started revisiting old archival data, hoping that perhaps the object had already been photographed by accident without anyone realizing it. Even amateur astronomers joined the effort, using online databases, algorithms, and citizen science platforms to search for anything suspicious. For a while, it seemed that the more we searched, the more pieces of the puzzle began to fall into place. More extreme trans-Neptunian objects were discovered. Some of them showed similar orbital alignments. A few even had retrograde orbits, moving in the opposite direction from most other objects. And once again, the mathematics pointed to the same possibility: something large, extremely distant, and hidden in the darkness. But there was a problem. No one had ever actually seen Planet 9. Years passed. New predictions appeared, and more regions of the sky were ruled out. But every image, every sky survey, every attempt to locate it ended with nothing. Yet the clustering of the orbits remained real. And every time a new trans-Neptunian object was discovered that fit the same pattern, the theory became a little more convincing. At this stage, it still wasn't proof. But it was enough for Planet 9 to become one of the most widely discussed ideas in planetary science, not because it sounded exciting, but because it explained the mathematics better than anything else. Still, not everyone agreed, and this is where things started to become more complicated. The idea of Planet 9 didn't remain unchallenged for long. In science, it never does. As soon as the hypothesis gained attention, researchers around the world began testing it. Some tried to confirm it, others tried to disprove it. That's how science works. If something is truly correct, it must survive every attempt to prove it wrong. So what did scientists do? They began running computer simulations, a lot of them. Using powerful models, researchers recreated the solar system. But this time, they added a hidden ninth planet far beyond Neptune. They assigned it the predicted mass, distance, and orbital shape suggested by the theory. And in many cases, it worked. The simulations reproduced the same kinds of orbital clustering that we observe in real data. The strange behavior of those distant icy objects became much easier to explain when Planet 9 was included in the model. But then, the first serious objection appeared. Some researchers, including Samantha Lawler and Jean-Marc Petit, suggested that this orbital alignment might not be caused by a hidden planet at all. It might simply be a coincidence. Their argument was straightforward. The number of known objects is still relatively small, and most of them were discovered by only a few survey programs that observed the same regions of the sky at roughly the same time of year. This could have introduced a certain bias. If you only look in one direction, you will only find objects pointing that way. It's like standing in a forest with a flashlight, shining it at one spot and saying, "All the trees are in that direction." Maybe, or maybe that's simply where the light happens to fall. This led to growing disagreements among scientists. Some researchers remained confident, arguing that such consistent orbital alignment was far too stable to be a coincidence. Others were not convinced. They wanted more precise data, a larger number of objects to analyze, and wider coverage of the sky before accepting the existence of an entirely new planet. Meanwhile, new simulations were being carried out, not only to support the Planet 9 hypothesis, but also to test alternative explanations. One group of scientists suggested that the unusual orbits might be caused by a massive disk of small objects acting together, collectively producing a gravitational influence, a kind of gravitational soup affecting surrounding bodies in bulk. Another group proposed that passing stars in the early history of the solar system might have disturbed the orbits of these objects. There is also a small group of researchers who support modified gravity theories. They argue that perhaps we don't need a planet or even a massive disk at all. Maybe gravity itself behaves differently at extremely large distances. Most scientists don't support that last idea. But the point is that Planet 9 was never the only explanation. It was simply the cleanest hypothesis, the one that matched the mathematics most convincingly. Still, the longer it remained unseen, the more critics began asking the same question. If it's really out there, why haven't we seen it yet? Over time, that question grew louder, especially because, despite increasingly precise predictions about where Planet 9 should be located, telescopes kept finding nothing. Vast regions of the sky were examined, and still, nothing. The theory wasn't completely disproven, but it wasn't growing stronger either. It found itself in a strange position. There was still no better explanation for the clustering of orbits, yet the lack of direct evidence was starting to wear down the patience of many scientists. That's how things stood for a while. Then something unexpected appeared. Not in the sky, but in old data collected decades ago, and it changed the story. For a theory that began with so much excitement, the search for Planet 9 eventually ran into a wall, not because the mathematics failed, but because the sky simply refused to cooperate. After the hypothesis was published in 2016, Astronomers around the world began scanning the regions of the sky where Planet 9 was predicted to exist. Brown and Batygin used models to estimate its orbit. Not an exact location, but a fairly reliable idea of where it might appear in the sky and how bright it might be. That was enough to launch a series of targeted searches using some of the best tools available. Among them were the Pan-STARRS telescope system, the Subaru telescope, the Dark Energy Survey, and archived observations from the WISE mission. But they found nothing. Part of the problem is how incredibly faint Planet 9 would be. If it exists, it is likely hundreds of times farther from the Sun than Earth. As a result, it reflects almost no sunlight. At such a distance, even an object the size of Neptune would be nearly invisible to most telescopes unless you knew exactly where to look. In addition, Planet 9 would move extremely slowly. It would drift across the sky over weeks or even months. That means most software designed to detect fast-moving objects wouldn't notice it at all. Despite this, there was still hope that Planet 9 might have already been captured accidentally in older sky surveys. Perhaps it was there all along, simply unnoticed. So astronomers began digging through archival data. In particular, they examined observations from the IRAS mission of the 1980s, the Japanese infrared satellite Akari from the 2000s, and the WISE mission, a NASA infrared telescope that scanned the entire sky in 2010. These surveys didn't reveal a planet directly, but they left behind thousands of mysterious sources of thermal radiation, tiny blurry points that appeared to move slowly. The problem was that most of those points turned out to be distant galaxies, noise, or image artifacts. But what if one of them was something more? That possibility alone kept scientists interested. Even if it wasn't Planet 9, it raised an important question. How many unknown objects might still be hiding in this region? What else could be out there that we simply haven't noticed? Meanwhile, other surveys continued narrowing the search area. In 2021, a research team analyzed data from the Zwicky Transient Facility, which had spent years capturing wide-field images of the northern sky. They filtered the data for slow-moving objects with the appropriate brightness and distance. The result was significant. They ruled out more than half of the region where Planet 9 was expected to exist, at least for objects brighter than magnitude 21.3. Later, results came from another, less widely known but highly specialized survey called Cameo 14. It also found nothing. That meant one thing. If Planet 9 truly exists, then it must either be extremely dim, hiding somewhere in the far southern sky, or its orbit is so different from what we predicted that we have been searching in the wrong place all along. In other words, the evidence didn't disappear. But the trail went cold. The more we searched, the more possibilities we ruled out. That isn't failure. That's how science works. But it also meant that the number of places left to look was shrinking until something new appeared, not just in the data, but in the real sky. A strange, newly discovered object that raised an entirely new set of questions. After years of dead ends, the last place anyone expected progress was in old data from cold, outdated satellites. Yet that is exactly where the most intriguing lead appeared. These satellites were never designed to search for planets. Their purpose was to scan the sky in infrared light, looking for stars, galaxies, dust, and sources of heat. But because their surveys were so deep and wide, their databases became a kind of digital fossil bed, a place where something missed during the first analysis might still be hiding. That doesn't mean Planet 9 is ruled out. It just means that not everything weird in the outer solar system can be automatically blamed on it. Still, it's hard to ignore the fact that 2017 of 2011 exists. Something put it there. And whether that something is Planet 9 or a passing star from millions of years ago, or even just long-term gravitational drift, it's a clue, but not the kind that solves the puzzle, the kind that makes it harder. This discovery also added weight to a different idea. Maybe we're looking for one big planet when the truth is messier. Maybe there's a population of medium-sized rogue objects out there, not massive enough to be planets, but enough to stir things up. If that's the case, Planet 9 might not be real, but its effect could be. At the very least, 2017 reminded everyone of this. We still know very little about what's out there. Every new discovery adds data, but not always clarity. Sometimes, the mystery just gets deeper. Let's say Planet 9 is real, a massive world 5 to 10 times the mass of Earth orbiting hundreds of times farther from the Sun than we are. The next question is simple. How did it get there? Because it shouldn't be there. According to how planets normally form, there simply wasn't enough material that far out in the solar system to build something so massive. Beyond Neptune, the Sun's influence weakens. The disk of dust thins out and everything slows down. You might get icy rocks or comets forming, but full-blown planets, that's a stretch. So, if Planet 9 didn't form out there, where did it come from? One of the leading ideas is that Planet 9 formed much closer to the Sun, maybe somewhere around the same region as Jupiter or Saturn. During the early chaotic days of the solar system, planets were constantly pushing and pulling on each other, exchanging angular momentum like bumper cars in slow motion. In that chaos, it's possible that Planet 9 got kicked out, flung into the outer solar system by a gravitational interaction with one of the gas giants. But instead of flying off into interstellar space like most ejected planets would, something unusual happened. It got caught. It didn't escape completely. It ended up in a highly elongated, stable orbit far beyond the other planets. It became a kind of solar system exile, too far to be seen, but close enough to remain bound by the Sun's gravity. This idea isn't just a guess. Computer simulations have backed it up. When researchers run dynamical models of early solar system formation, they often see outcomes where one or two planets get kicked out into distant orbits. Some even end up in orbits similar to what Planet 9 is supposed to have. It's not the most common result, but it's not rare either. According to some simulations, about 1 in 10 early solar systems could end up with a Planet 9-like object. But there's another scenario, one that's even more interesting. Instead of being born in our solar system and thrown outward, maybe Planet 9 was never ours to begin with. Imagine the early Sun forming inside a dense stellar cluster, surrounded by dozens or even hundreds of other baby stars, all forming from the same cloud of gas and dust. In that crowded nursery, planets and debris would have been flying everywhere. And in those chaotic conditions, it's entirely possible that our Sun stole a planet from another star. This idea, called planetary capture, isn't just theory. Simulations show that in a dense cluster, passing stars can grab rogue planets or even rip them from each other's orbits during close encounters. If Planet 9 was originally orbiting another star and our Sun passed close enough at the right time, it could have been pulled into our system and trapped in a wide, distant orbit. In fact, one study showed that the chances of capturing a planet like that during the solar system's first 100 million years could be as high as 20%, if conditions were right. This kind of scenario also helps explain why Planet 9's orbit, if it exists, is so tilted and stretched. It didn't form in the neat, flat plane of the solar system. It came in from outside, and that means its orbit wouldn't match the rest. It would be inclined, odd, unpredictable, just like the clues we're seeing now. Some researchers think both ideas could be true. Maybe a planet formed in the early solar system got pushed out and then got nudged further by a passing star, or maybe several small interactions added up over time. Space doesn't always give us one clean answer, but the key point is this: there are ways Planet 9 could exist, and they're not unrealistic. They don't break physics. They don't require rewriting how planets form. All they require is time, chaos, and gravity. 3 things the early solar system had plenty of. So, while we haven't found Planet 9 yet, we know it could be there, and we know how it could have gotten there. The only thing we don't have is the proof yet. After nearly a decade of theories, simulations, and dead ends, the search for Planet 9 is approaching a turning point. Not because someone spotted it yet, but because the tools we've been using so far have reached their limits. We've scanned most of the visible sky, combed through decades of archived data, and ruled out large chunks of where Planet 9 could be, and still nothing. That's where the Vera Rubin Observatory comes in. Located in Chile, this observatory hasn't been fully operational for long, but when it is, it could change everything. Rubin is different from most telescopes. It's not designed to zoom in on one target at a time. Equipped with an 8.4-meter Simony survey telescope and the world's largest digital camera, it will survey the entire southern sky, night after night, in incredible detail. Its primary mission is called the Legacy Survey of Space and Time, LSST. And it's exactly the kind of project that could finally spot a slow, moving faint object like Planet 9. Why? Because Rubin is fast. It can capture huge portions of the sky in a single shot. And it's deep, sensitive enough to detect objects much dimmer than what older surveys like ZTF or Pan-STARRS could handle. Most importantly, Rubin will observe the same regions of sky repeatedly over a 10-year stretch. It's not designed to zoom in on one target at a time. Equipped with an 8.4-meter Simony survey telescope and the world's largest digital camera, it will survey the entire southern sky, night after night, in incredible detail. Its primary mission is called the Legacy Survey of Space and Time, LSST. And it's exactly the kind of project that could finally spot a slow, moving faint object like Planet 9. Why? Because Rubin is fast. It can capture huge portions of the sky in a single shot. And it's deep, sensitive enough to detect objects much dimmer than what older surveys like ZTF or Pan-STARRS could handle. Most importantly, Rubin will observe the same regions of sky repeatedly over a 10-year stretch. That means it won't just find fast-moving asteroids or comets. It'll catch the slow drifters, the ones barely moving across the sky, the ones like Planet 9. Based on current estimates, Rubin could detect objects as faint as magnitude 24. If Planet 9 is within the predicted mass range and anywhere inside about 800 astronomical units, it should be bright enough to fall within Rubin's reach. Which means if it's out there and it's not hiding behind the galactic plane or buried in background noise, Rubin should see it. And if Rubin doesn't find anything, that's big too. It won't just be no news. It'll be the strongest evidence so far that Planet 9 either doesn't exist or exists in a way we didn't predict. Maybe it's smaller, farther, or has an entirely different orbit than we thought. In other words, Rubin is more than just another telescope in the search. It's the final test, the one that could end the mystery one way or another. But the search doesn't stop with Rubin. While it's the most promising tool we have right now, other efforts are still running in parallel. Projects like Backyard Worlds, Planet 9, continue to enlist citizen scientists to look through telescope data, sometimes spotting things that algorithms miss. There are also upcoming space telescopes like Nancy Grace Roman and Euclid that could help indirectly by refining our models of the outer solar system and improving the background maps we use to detect faint motion. And then there's the wild card. Maybe Planet 9 has already been seen, but not recognized. Maybe it's in old data, mislabeled. Maybe it's hidden behind the dense clutter of the Milky Way, where background stars and dust make motion hard to track. Or maybe it's just dimmer than we expected, smaller, colder, darker. All of these are still possibilities, but what Rubin gives us is something we haven't had before. A clean, deep, continuous survey of the southern sky. And that's exactly where Planet 9 is most likely hiding according to the latest models. So, for the first time in years, this isn't just about chasing a theory, it's about reaching a decision point. If Planet 9 exists, we're about to know. If it doesn't, we can finally let it go. And that's what makes this next phase so important. Because it's not just about finding a new planet, it's about finishing the story. In early 2025, a fresh analysis of the IRAS and Akari archives revealed something unusual. It was small, it was faint, but it appeared in both sets of observations taken roughly 20 years apart. And more importantly, it was moving. Very slowly, but it was moving nonetheless. That motion was the key. Galaxies don't move like that. Stars don't either. And image noise certainly doesn't. But distant objects in the solar system do move that way, especially ones as far away as the predicted Planet 9. At first glance, it looked exactly like what astronomers had been waiting for, a possible direct detection. The object wasn't bright, but its properties matched what you would expect from a cold planet located hundreds of astronomical units from the Sun. Its infrared signal also seemed just right. Not hot, not noisy, only slightly warm, like a frozen world slowly radiating leftover heat. Naturally, this sparked a surge of interest. News headlines quickly picked up the story. Articles began speculating. Could this finally be the long-awaited confirmation? But the excitement didn't last long, because the orbit didn't match. Planet 9's predicted orbit is elongated but relatively flat, tilted roughly 15 to 30 degrees from the main plane of the solar system. The new object's orbit, however, was tilted by more than 120 degrees. That's not just a small difference. In fact, it was moving almost upside down compared to most other objects. Its orbit was retrograde, meaning it traveled in the opposite direction to most planets, and its inclination was far greater than anything ever predicted for Planet 9. And that became a problem. Could Planet 9 have an orbit like that? Technically, yes, anything is possible, but it would mean completely rethinking all the original models, the same ones that explain the clustering of distant objects. In that case, they would no longer account for the same patterns. And if it doesn't explain the orbital clustering, it can't be Planet 9. It would have to be something else entirely. Mike Brown, one of the original proponents of the Planet 9 hypothesis, quickly stepped forward to clarify. He stated that this was definitely not the Planet 9 they were searching for. In his view, the object is real. It could be a large trans-Neptunian body, or perhaps something we haven't classified yet, but certainly not the planet astronomers have been trying to find all these years. So, in a strange twist, the most intriguing object discovered in a decade might not solve the mystery. It might deepen it. Because now we have two problems. We still haven't found Planet 9, and at the same time, we've discovered something else that doesn't fit the model at all. That's the uncomfortable position this discovery leaves us in. It's progress, but in the wrong direction. Still, not everyone sees it as a dead end. Some researchers argue that this simply shows how little we truly understand about the outer solar system. Perhaps there are dozens of unknown objects like this out there. Maybe Planet 9 isn't the only one. Maybe the solar system is far stranger than we imagined, and we've only begun to uncover its real structure, and that raises an even bigger question. If we're finding strange things simply by revisiting old data, what else might we have missed? Because even if this object isn't Planet 9, it proves one thing. There is something out there. While attention was focused on the mysterious infrared object, another surprise emerged from the distant edges of the solar system. This time, not from old data, but from a completely new discovery. The object was designated 2017 OF201. At first glance, it didn't seem particularly remarkable, just another distant dwarf planet added to the growing list of extreme trans-Neptunian objects, but its orbit immediately drew attention. This object followed an extraordinarily elongated trajectory that stretched nearly 1,600 astronomical units from the Sun at its farthest point. For comparison, the orbit of Pluto reaches a maximum distance of only about 49 astronomical units. This object was essentially operating in an entirely different region of the solar system. Its orbit wasn't just distant, it was extreme, long, stretched, and sharply tilted. The kind of orbit that seems to say, something powerful must have thrown me out here. Naturally, people ask the obvious question. Could this be another piece of evidence for Planet 9? At first, it seemed possible. After all, the Planet 9 hypothesis predicted exactly these kinds of orbits, where gravitational influences over millions of years gradually fling objects into strange, highly elongated paths. So 2017 OF201 looked like the kind of smoking gun everyone had been waiting for. But closer analysis revealed something different. Its orbit didn't match the same cluster that the original Planet 9 theory was built on. In fact, 2017 OF201 appeared to operate under an entirely different pattern. It wasn't aligned with the other objects. It didn't reinforce the pattern. It broke it, and that created a new problem. If Planet 9 is supposed to explain the clustering of extreme objects, yet we keep discovering new ones that don't fit the pattern, does that weaken the hypothesis? That's where the uncomfortable part begins. Every new object we discover in the distant solar system should, in theory, either strengthen or weaken the case for Planet 9. The more objects that follow the expected pattern, the more convincing the theory becomes. But when something large like 2017 OF201 appears and doesn't fit, it starts to raise doubts. Are we truly seeing a consistent gravitational influence, or are we simply selecting the objects that support the theory while ignoring the ones that contradict it? Some researchers have begun suggesting that the pattern itself might be a statistical illusion, a form of observational bias caused by where and how we search the sky. They argue that 2017 OF201 is exactly what you would expect if Planet 9 doesn't actually exist. Just a large collection of random orbits scattered over billions of years through minor gravitational interactions, galactic tidal forces, and chaotic motion.